Bismillah ar-Rahman ar-Rahim. Welcome to tutorial number 6. In this tutorial we're gonna have 3 problems. The first one, it says that for the circuit shown in figure 1, design a band pass filter. Okay, so we need to design band pass filter with the cutoff frequency omega naught and bandwidth of 25. This is part A, and then part B, we need to determine the quality factor and the bandwidth for the whole circuit. So let us first of all design the band pass filter, which is this one. That means we need to find the value of L and the value of R. And omega naught is given, so we know that XL will be equal to XC, and we know that XL is equal to omega L. Of course, at the cutoff will be equal to 1 over omega naught C. Then we can find the value of the inductance. The inductance factor as well can be obtained from XL, okay, at the cutoff frequency divided by R, right? So once we determine the value of the Q from this equation, because we know the bandwidth, we know omega naught, we can obtain Q. So now we know Q, we know the value of XL at the cutoff frequency, so that will give us the value of R. Therefore, the value of the resistance will be equal to 80 ohm. Now, for the to determine the quality factor for the whole system, so what we need to find, we need to find the what will be the total resistance, because again the quality factor will depend on the resistance. So what will be the total resistance? We have the 320 ohm, which is the load, and then the value of R, which is the one component of the filter, which is already calculated as 80 ohm. So now we have 80 ohm in parallel with, we have 80 ohm in parallel with 320, and that will be in series with 36. So that will give us the overall resistance in this circuit. Okay, and then of course we know the value of XL at the cutoff frequency. So we know the R, we know XL, and then we can calculate the quality factor for the whole system, as it is mentioned over here. And of course also we can calculate the bandwidth by using the equation that bandwidth will be equal to omega naught divided by quality factor. So omega naught is given, quality factor is already calculated for the whole system, so that will give us the value of the bandwidth, and that will be equal to 31.25 kilo radians per second. Okay, so this is with regard to the first question. Now let us move to the second problem. In the second problem, it says that use MATLAB Simulink software to simulate the system shown over here. So we have a voltage source, and that provide the power to a resistance which is 100 ohm, but the voltage source of course is not sinusoidal waveform. So now we need to create this one by using MATLAB. So we're gonna go to the MATLAB. Okay, so this is the circuit that will create that waveform. So over here we have a controlled voltage source, and that will be controlled by using the following table. Okay, so that will provide that kind of a voltage waveform that we saw already in the problem. This is the resistance 100 ohm, and we need to monitor this one, the voltage across the resistance, by using the oscilloscope. Let us simulate this one in MATLAB, and now we at the how the waveform look like. So just yes, it is just like what we saw in the problem. Okay, this is for the first part, which is say that use MATLAB to simulate the circuit. Now let us look at the second part. Say that display the output voltage harmonic spectrum. So we like to look at the harmonic spectrum. How to do the harmonic spectrum? By clicking on this icon over here, go to Tool, and then go to FFT, Fast Fourier Transform. Click on that, and that will give you the signal. Okay, now if we like to do the Fourier, just you will click over here on the display, and that will give you the harmonics. So the total harmonic over here is 48%, and you can see that this is the fundamental component, the third harmonic, the fifth, and so on. Okay, so this is with regard to the first one. With regard to the second question, he said design a notch filter to bypass the third harmonic. Notch filter. Okay, so we know that the notch filter will consist of 3 elements, R, L, and C. Okay, so we're gonna have L, C, and also we're gonna have R. So this is how the notch filter look like. Okay, so now if we look at the our circuit, our initial circuit, this is our initial circuit. So now what we need to do, we need to put a filter to get rid of the third harmonic. Okay, so such that when we do the Fourier analysis, the third harmonic will be taken out. So this, here we go. Here we have to put the notch filter, which consists of L, C, and small resistance. So this is what we need to add in our circuit. Now what will be the value of L? What will be the value of C? What will be the value of R? That we call it design. Okay, so specifying or determining those parameters, that we call it filter design. Okay, of course, nothing is given to you in this problem, except that he said that design a filter to get rid of the third harmonic. So only we know H, which is 3. Of course, we know that at resonance, XL also will be equal to XC. So that means omega L will be equal to 1 over omega C. Therefore, to find C, we need to find L. Maybe has to be given or assumed. So we can, for example, over here, what we can assume, or what I have assumed, that let us take L to be 1 millihenry. So that will give you directly the value of C. Once you specify L, then you can determine the value of C. Of course, also to find the value of the resistance, if no more information is given, then it can be assumed. So maybe you can assume it to be 0.5 ohm, 0.4 ohm, 0.1 ohm. So you can assume a value, look at the simulation result, and then you can retune those values until you obtain I can say good result. So maybe I can assume it to be 0.1, somebody else will assume it to be 0.5. Okay, now if we do this one in MATLAB, of course we can do the same process as before. You're gonna obtain this kind of result. Okay, Okay, so this is LCR. Okay, so we know that we like to get rid of the third harmonic. So then omega will be 2 by f times 3, and then let us assume L to be 1 millihenry. That will give you the value of C. Also, you can assume R to be 0.1, 0.2, 0.3. That will be also fine. Now, if you put those value in MATLAB, okay, you're going to obtain those results. So again, this one will be this is how the output voltage will look like. Don't forget, the initial voltage was just like over here we have something like 100, which is constant, and it will jump to minus 100, right? That was our initial waveform. We have something like that, then do something like this one. But now, of course, the waveform change because we place a filter. Now, if we look at the how the harmonic analysis look like, we're gonna have this kind of wave of harmonic. So you can see that third harmonic is out roughly. There is no third harmonic because now in the circuit we place a filter, and that filter took out the third harmonic from the output voltage. And you can see that also the total harmonic distortion was reduced. Okay, now it is 34.5 and it was something like 48. Okay. If we continue with the problem, let's say that in the second part, or in part C, say that design multiple frequency trap filter to bypass not only the third, but now you need to design a filter to get rid of the fifth harmonic, the seventh, the ninth, and the 11th harmonic. And then you need, of course, to obtain the output voltage harmonic spectrum. And then you need to sketch what we call it Z-scan, so to find what will be how the impedance will look like. Okay, so don't forget that if we have series resonance, so the impedance will be very small. If we have parallel resonance, the impedance should be very large, right? So this is inshallah what we're gonna obtain also. So you can just add over here another filter to get rid of the fifth, seventh, and so on. If you do that, you're gonna have this kind of circuit. Okay, so this is the filter for the third harmonic, fifth harmonic, seventh, ninth, and so on. And again, you can assume L to be the same, then you will calculate the value of C, and then you can do simulation by using MATLAB, and you will obtain the following results. So this is how the voltage will look like after we place a filter to get rid of the third, the fifth, seventh, ninth, 11. This is how the waveform will look like. And now if we do Fourier analysis for the signal, this one will be the result. And now let us look at the result. There is no third, there is no fifth, there is no seventh, ninth, 11th, nothing. And we able to reduce the total harmonic distortion from, it was 30 something, now it reduced to 20%. Okay, so this is the way that can be utilized to design a filter to get rid of some harmonic. Okay, let us go back to the question. So do we need to do any more calculation in this question? Yes, and of course we need also to sketch Z-scan. So how to sketch Z-scan? Actually in MATLAB we have what we call it Z. Let me show you this one in MATLAB. So if I just open MATLAB now, okay. So what we have in MATLAB, we have in MATLAB what we call impedance measurement. Okay. So we have impedance measurement. So just you need to put that measurement in parallel, let us say at the load, if you are interested, to find the impedance of the system, and that will give you the result. So once you finish from simulation, again you need to click on this one, go to tool, and you will find that over here impedance measurement. Okay, and then you can obtain the waveform of the impedance. Of course, this is a different example, but if we are looking at this result over here, for example, for the third harmonic, you can see that the impedance at the third harmonic, which is when the frequency equal to 150, it dropped to a very small value because XL and XC are the same. Then we're gonna end up with only resistance, right? In the circuit, we're gonna end up with only resistance, and the resistance, of course, is very small. Once we design the filter to get rid of the third, the fifth, the seventh, the ninth, and the 11th, also we're gonna have the impedance as it is shown over here. So this is how the impedance look like. See that? So at the third harmonic, the total impedance of the system at the third harmonic become unresistive at the fifth, at the seventh, at ninth, and so on. Okay. The last part in this example, say design a band pass filter to block the harmonic. Okay, display the output voltage harmonic spectrum after adding the filter, then verify the correct tuning of the filter by using Z-scan. Okay, so the first, again, over here in part B and C, we design what we call it notch filter. But now we need to design what we call band pass. So it need only to pass mainly the fundamental component. It need to pass only the fundamental and to block the other harmonic, right? We like to minimize the third, the fifth, the seventh, the ninth, and the 11th. So we need to bring those down and to allow mainly the fundamental component to go to the load. Okay, so this is what we need to do now. So we need to design a band pass filter. Now, how the band pass filter look like? Well, band pass filter look like this one. Okay, let me show it to you in also in MATLAB. Okay, so over here, this is our filter. Okay, so this filter, it need to block all harmonic, or most of the harmonic, and to allow only the fundamental component to go through. Okay, so we call it again a band pass filter. Now, how to how to do that in simulation. Let us do it in MATLAB. Okay, so this is our filter. This one will be our filter. Mean it is L and C. And now, and of course, how can we calculate the component of L and C? It's like what we did before. Okay. So again, we like this filter only to pass the fundamental component. Okay, so it will pass only the fundamental component. So at of course, I mean the fundamental component will be 50. Okay, so then 2 by f will be that value, and again we can assume a certain value for the inductance. Let us assume the inductance to be equal to 1 millihenry, and then we can calculate the capacitance. That will be 11 millifarad, and then let us say that we choose R to be 0.1 or 0.2 or even 0.5. Okay. And then we need to do the simulation. So once we determine the value, of course this is R1. Okay, actually it will make no difference. So those are the component of the filter. Mainly we have L, we have C, and we have R1. If we do the simulation in MATLAB, again this is the MATLAB file. Okay, so this is our voltage source, this is our load. So of course I guess I connect over here a meter to measure the current. I connect over here, let us say another meter to measure the root mean square the volt of the source voltage, and so on. Okay, but those are the main components. So those are the filter component. Now let us do simulation. So click on simulation, finish. Okay. Now if we like to monitor how the voltage will look like in this case, so this is how the voltage look like. So you can say that the voltage waveform really it become like sinusoidal. Okay, so this filter, by putting band pass filter, we are able to block most of the harmonic. Most of the harmonic are blocked. We are able to pass mainly the fundamental component. So fundamental component went to the load, but the harmonics, most of the harmonic are not allowed to go to the load. Now if we like to do Fourier transform, so yes, let's just refresh. Okay, so this is our voltage across the load. And now if we like to do Fourier, so I guess we need to say draw. And now look at the total harmonic distortion. Total harmonic distortion dropped from around 20 to around 9.4, only 9.4. And most of the harmonic, it is only fundamental, because I mean the fundamental is huge. Okay, fundamental is very huge value, whereas look at the third harmonic, it is very small compared with the fundamental, right? So of course still we have harmonic, but their percentage is very low. Okay, and again if we like to see the impedance measurement for this case again, so I guess we need to click on the impedance measurement, and this is how the impedance will look like. So you look at the fundamental frequency. At the fundamental frequency, the impedance is so small, so then that means the filter will allow mainly the fundamental frequency component to be transferred to the load, and it will block most of the harmonic. Okay. Okay, of course, the result is given to you over here in the tutorial. Okay, that's all. Thank you.